Welcome to the last video in this series of 5 about graphing trigonometric functions. Here we consider a concept of phase shift, where trigonometric function graphs shift left and right. Here's our first of two examples. Suppose we wanted to graph y equals the sine of x plus pi over 6. The first thing that we would do is pull from memory our sine function. And then, with the understanding that the transformation here is going to be a leftward shift of pi over 6, which you may recall from the graphing via transformations video, and we essentially just have to shift this entire graph left pi over 6 spaces. So, because every single point on this graph is going to shift left, let's just consider 5 very important points on this graph and shift them to the left. We'll start with 0. The sine function goes through the origin. For our new function, y equals sine of x plus pi over 6, that point is going to shift left pi over 6 spaces. If you're wondering why I chose that exact distance there to represent pi over 6, one way to think about it is that the distance from 0 to pi is pi, and I took about 1/6 of that distance to determine how far to go over. Well, let's continue looking at 5 important points on the sine function. Let's now look at the local maximum here. That too will shift left by pi over 6 spaces to create the local maximum of the new function. So I'll shift that left pi over 6 spaces. If you're wondering where I got pi over 3, it was pi over 2 minus pi over 6. I subtracted pi over 6 from the old x value of the local maximum. Here's another important point on the sine function, and that too we can shift left pi over 6 spaces. So that would be pi minus pi over 6. I worked out pi minus pi over 6 on scratch paper and got that. And that's going to be our new x-intercept for the function we're currently graphing. Continuing along those 5 important points, let's look at the local minimum of the first period of the sine function. That also will shift pi over 6 spaces to the left. If you're wondering where I got 4 pi over 3, I did 3 pi over 2 minus pi over 6. And lastly, the end of the period, 2 pi, will shift left pi over 6 spaces. 11 pi over 6 came from 2 pi minus pi over 6. And so now these 5 new points, you may see them in red, are the same important points on our new function. Those are the x-intercepts and the local extrema. So all we have to do now is draw a sine function that goes through our new 5 points, and we have effectively shifted the graph pi over 6 spaces to the left. It's a tradition in the graphing of sinusoids to label the local maximum, local minimum, and to not clutter the graph with additional information. So I will label those points, and I now have a perfect one-period graph of the sine of x plus pi over 6. Now, something to ponder before we look at our next example. Does this function start at negative pi over 6 and end at 11 pi over 6? Well, I've graphed that as my beginning and end points. But let's not forget that this function continues to go on forever, repeating this way in both directions infinitely. So the understanding here is, when we graph one period of this function, the reader understands that there are infinitely many of these propagated in either direction to form an infinite sine wave. Let's look at another example of phase shift. So if we want to graph this cosecant function, say, then we have to first examine what the ordinary cosecant looks like. You'll recall this from a prior video. Now, one would think that because of the 2 in front of the x, that we would have a horizontal compression by a factor of 2. Maybe. One would also think, because we're subtracting pi over 2 inside the function, that we would have a rightward shift of pi over 2. Maybe, but it turns out that there's a special rule in graphing of transformations that's so unusual and rare that I didn't even mention it in that series of videos. And that is this: when you have these two competing transformations inside of the function, a multiplier of the variable followed by an addition or subtraction, again a rare situation but one that we're encountering here, there's a rule that you can't apply the transformation rules in that situation. What can you do then? Well, what you have to do is factor out the 2 inside of the cosecant argument. When you do that, it looks like this. Now, this probably looks strange to you. Let me highlight the important portion of this. What we've done from the top argument is factor the 2 out, thereby changing pi over 2 into pi over 4. If you're not convinced of this right away, try multiplying or redistributing the 2 back through the parentheses in the bottom expression, and you'll indeed get the top one. And it shouldn't be that surprising. After all, when we factor out a 2 from a polynomial, don't we cut all the coefficients in half inside? And isn't half of pi over 2 pi over 4? So that's the strange algebra that we have to perform here, because it turns out if the coefficient of x is factored out, in this case only, then the rules of transformations apply. So this 2 is going to be a horizontal compression by a factor of 2. And this subtraction here now represents our rightward shift, which is going to be pi over 4, not pi over 2 like you might have thought from the way that this was expressed originally. So here's our task now. We have to take this cosecant graph, you may see it in gray, and we have to do a horizontal compression by a factor of 2 and then a rightward shift. You follow the order of operations much like you would an ordinary expression, multiplication before subtraction. And so first we're going to compress this by a factor of 2. What does that mean? That means that every point on this graph is going to be compressed in towards the y-axis to half of its original distance. Now, if that's happening to all points on the graph, it would suffice for us to just track the important things, like the asymptotes and the local minimum and maximum. Because if we can track what happens to those particular features of the graph, then the rest of the graph will just fall naturally into place. I'll show you what I mean. First of all, let's go from left to right here. The cosecant has a vertical asymptote of 0. You don't see it as a dotted line because it's on the y-axis. Well, if something is at 0 and then it gets cut in half, it's still at 0. So we're going to still have a vertical asymptote at 0. It's not surprising that something that is on the y-axis, when it gets compressed half the distance to the y-axis, it's still on the y-axis. If you lost that one, that's okay. Watch and you'll see a pattern. So next I'm going to focus on this local minimum. This local minimum has an x value of pi over 2. In our new compressed function, it's going to be half the distance to the y-axis, which in this case is pi over 4. That's half of pi over 2. Let's continue to track our way across. The cosecant graph has an asymptote of pi. When compressed in half the distance to the y-axis, that's going to be at pi over 2. Next, let's focus on this local maximum. The cosecant has a local maximum at 3 pi over 2, but that's going to shift half the way to the y-axis. Half of 3 pi over 2 is 3 pi over 4. And finally, the original cosecant has a vertical asymptote at 2 pi. You see it on the right of your screen. That too is going to compress into half the distance to the y-axis, putting it at pi. And now erasing the cosecant graph here, we can now see the compressed features of our new graph and fill in accordingly. By the way, we're not done with this problem. What we have done here is we've graphed y equals 2 cosecant of 2x. In other words, we've handled the horizontal compression by a factor of 2. Now that I've done that, let's turn our attention to a rightward shift of pi over 4. Now again, every single point on this graph, all infinitely many of them, are going to shift to the right by pi over 4. But if we just focus on the important features, the asymptotes and the local extrema, and we can find out where those will end up after a rightward shift of pi over 4, then we can easily draw the new graph as it will sort of follow along with those key features. So let's work our way left to right. The current graph, you may see it in green, the current graph has a vertical asymptote at 0. That's going to shift over pi over 4 spaces to here, which would be pi over 4. The cosecant 2x, again, you may see it in green, has a local minimum at pi over 4. That's going to shift over by pi over 4, which will bring it to pi over 2. The cosecant of 2x, or the green graph, has a vertical asymptote at pi over 2. That's going to shift over by pi over 4. Pi over 2 plus pi over 4 works out to be 3 pi over 4. The cosecant of 2x, or the green graph, has a local maximum at 3 pi over 4. That's going to shift over by pi over 4. 3 pi over 4 plus pi over 4 is pi. And finally, the green graph, or the cosecant of 2x, has a vertical asymptote of pi. That's going to shift over by pi over 4. Pi plus pi over 4 is 5 pi over 4. And now erasing the so-called old graph, I can see that my shifted features, the asymptotes and the local maximum and minimum, show me as a guide where the rest of my function is going to be. And now I'm essentially done with this problem. Although, just to be traditional here, I'm going to express the local maximum and local minimum as ordered pairs rather than marks on the x-axis. Same information, and I now have y equals the cosecant of 2x minus pi over 2. And that completes this video and this series on graphing trigonometric functions.